Now, the last presentation before lunch is going to be held by Raoul Schaffranek. I hope I pronounced your name correctly, from Runtime Verification, and he's going to be talking about using a solidity debugger to explore time and space. Let's welcome him with applause.
Hi, everybody. My name is Raoul Schaffranek. I'm a former verification engineer at Runtime Verification. And it's my pleasure today to present to you the newest addition to our formal methods tool suite. So at RV, we get the feedback a lot that formal methods sounds really useful in theory, but it's not really, it's too complicated, basically. And so we took this feedback seriously, and we invented this new tool that is meant to lower the entry barrier to formal methods and basically enable every developer and every security researcher to apply formal methods to their smart contracts. So I can do a lot on this stage to convince you of how cool our new tool is, but I actually want to encourage you to go to our public website. We just released a public demo version. You don't need to install anything on your computer. It runs completely in a browser. So just go to this website, it loads a Visual Studio Code instance, and you can start debugging wrapped ETH with our newest tool. But let's provide a little bit of background theory. So you might have heard that solidity, or the EVM, is a state machine. But what does it mean? So basically, we have states that are composed out of the accounts storage, accounts code, the balances, and then we have transactions, which are the transitions of these of this transition system. So let's lay out the transaction history of Ethereum on a timeline. Like in 2015, the Genesis block was mined. So this is the initial state of our transition system. And then we sequenced like 1 billion of transactions. And now we are here. At this point, Ethereum is in some state, but we also know that in the past there have been some buggy states and then have been exploited. So as a security company, our goal is to make these exploits and vulnerabilities less common and protect ourselves against them. But well, we have a problem. That is, well, if you look at the past, then Ethereum's transaction history is just a straight line. But if we are thinking in the future, then there's like so many things that could happen next. We cannot predict what will be the next transaction to Ethereum. It could be anything, really. It could be someone making a swap on Uniswap. It could be someone staking on Lido. It could be someone bridging a token to Optimism. And then even after the next transaction, like if we could solve just this single problem, like the problem would repeat itself and we would have 1 billion more possibilities. And so we are branching out in an infinite space of possible states in the future. And this is a real problem. Like we noticed that smart contracts exploits gets more difficult. Like I don't know who remembers the Kyber swap exploit from last year. This was not a one transaction exploit, but it was an exploit that involved like long transaction sequences. So how can we safeguard our smart contracts against these long transaction sequences? How can we reason about our code confidentially that this cannot happen? And Symbolic's approach is, first of all, to collapse the state space of the next possible successor states. So at the top of the slide, we have some possible concrete transactions. It could be a transfer from Alice transferring 10 tokens to Bob, or Alice transferring 20 tokens to Bob, Alice transferring 30 tokens to herself. And all these transactions would end up in a different successor state. So what we do in Symbolic is we collapse these, like there are infinite many choices that you can make here. And what we do with Symbolic is we collapse all these possible concrete transactions into abstract transactions. So in yellow, on the bottom of the slide, you see an abstract transaction that starts from an abstract state where you see that the balances are just some variables, x and y, and then we are making a transfer from, and the receiver and the sender of the address of the transfer, they are also just variables. So same with the amount. And then we end up in only two possible successor states. Like one where the from and the to address are different, and one where the from and the to address are the same. So we collapsed the entire state space into a single abstract transaction. But now we still have this problem that we have possible multiple transactions, or we have vulnerabilities that only show in transaction sequences. So how do we solve this problem? And the cool thing is we don't need to introduce anything else. Like the approach that we showed before, like all these abstract states, they also make it possible for us to reason about transaction sequences. And the way it works is like, you see, when you have a transaction, a concrete transaction that is starting from some state, we abstract it in our abstract transaction and start from an abstract state that is more general than the first one. So we execute our abstract transaction and we end up in another abstract state. Now, the cool thing is that you can see that this final, or this abstract successor state is also subsumed in our initial state. So that basically means that we can reason about transaction sequences inductively. Like, that's a complicated mathematical term, but it basically means this transaction, this abstract transaction, does not care about what has come before. It does not care about the history. So in summary, we collapsed the problem of finding a bug in like an infinite amount of states and possibly very long transaction sequences to the problem of finding a bug in a single abstract transaction. So this also goes by the name symbolic execution. What else? So when we debug a transaction, it's not enough just to look at the predecessor state and at the successor state, right? We want to get insight into the transaction. We want to see where are things going sideways. So what we do is we break down a transaction into a finer granularity view. Basically, we can do this on two levels. On first, like every transaction is composed out of a solidity trace. So we can break down a transaction into a sequence of solidity statements that have been executed. So then our states are not anymore the accounts with all the balances and the storage, but our states become the solidity variables. And we can take this one level further. We can go even one level deeper and go to the EVM level. So every solidity statement can be decomposed into a sequence of EVM instructions. So on this level, our states become the Ethereum memory, the stack, the program counter, the storage. And our transitions on this deepest level become bytecode instructions. So how does it look like in our debugger? That was enough theory. So this is an Ethereum state or an EVM state that you see on the left, like this abstract state that I showed you. It has a program counter, a stack, and a memory. And in our debugger, you can see it in the variables view. So you can see that you can see what is the value of the program counter at the paused state. You can see what are the values on the stack, what's the memory. And you also notice that not all these values are concrete. Like there are some parameters here. For example, the call data here. Well, there's a function selector that is fully concrete, but what follows after is like a symbolic expression that tells us, well, whatever comes after, whatever the parameters of our functions are, in this case we are debugging the transfer from function, we make no assumptions about the source and the destination of the transfer from, and no assumption about the value. So we are actually executing it symbolically. And to build a little bit more on this metaphor about time and space. So there was, I think for me, like the personal best innovation that happened to debuggers over the last 10 years was the invention of time travel debugging. So time travel debugging allows you to step backwards through your code, execute your code backwards. That is very handy. Like usually you run into an exception and you want to see, okay, how did I get here? And then you just start executing backwards to trace down like the conditions that led you to this state. And we took this idea and took it one step further. So because we are able to reason about like alternative timelines, whatever comes next, depending on the inputs, we cannot just jump back and forth in our code, but we also can jump into alternative timelines. For simple example, like you have an if statement, and you are debugging the then branch, but you want to see what's going on in the else branch, and you can just select this branch from this nice little graph visualization that you see on the right-hand side on this slide. So, Symbolic, our debugger, is in its very, very early stages. We literally released the public demo just a few days ago. But we have very ambitious plans for this debugger. So we are aware that like Solidity is in general, it's missing a good debugger, like just a classical traditional debugger. It's not existent in Ethereum. There are some command line debuggers, but command line debuggers are not everybody's cup of tea. So we want to build out Symbolic into this nice little symbolic execution debugger, but we also want to emphasize on like concrete execution. So what we have right now is we have this open alpha version that you can check out. We have like all the things that you can expect from a classical debugger, like you can set breakpoints, you can step over the code, you can inspect the states, the call stacks. You can even like, there's a built-in disassembler, so you can even like disassemble your smart contract and see the bytecodes and step over the bytecodes one step at a time. That is very useful for like gas optimizers, for example. What's coming next is, and with next I mean within the next month, so in April, you can expect our open source release. So Runtime Verification is very committed to developing open source formal methods tooling, because we think that is the only way to scale formal methods and make it accessible for everybody. So expect our open source release soon. We are also working on a Foundry integration that would allow you to step through Foundry tests. We kind of have that working already, but just in the Symbolic case, we are now working like on a more seamless integration with the Foundry team to basically build out this concrete debugger. And what's still missing in our debugger is, like, well, you can inspect the call data, you can inspect the stack, the memory, but at the moment we cannot decode variables. Like, that's unfortunate, but this will come soon, so we will start building out support for decoding Solidity storage variables. And this nice visual graph that you saw on the last slide, this one, that's also not part of the public demo yet, but that will be released soon. And then after April, we have like several stretch goals that we want to reach. First of all, we want to make the developer experience even more smooth by decoding every and all possible Solidity variables, not only Solidity storage variables. And we are working with the Ethereum Foundation on this ETH debug format protocol. So Ethereum Foundation is building this ETH debug format protocol that is basically enabling us, is giving us all the information from the compiler that we need to make this translation back from EVM data structures to Solidity data structures. And then, well, we have a debugger working in a web browser, which is really, really cool. And we are thinking of building it out into like a mainnet transaction debugger, where you just go to Etherscan, you copy some transaction hash paste it into the debugger, and then you can actually replay the transaction of the mainnet inside your debugger, all in a browser. Okay, some shameless advertisement on my side. So we are currently hosting or co-hosting a Securum race. Like for those who are not familiar with these Securum races, they're basically just small quizzes. They take you 16 minutes to fill them out. And the top 32 participants will be invited to a workshop at Runtime Verification. This workshop will not only showcase symbolic and teach you how to use it, but it will also contain other tools on our like formal methods tool suite. For example, Control, which is like our symbolic testing framework. Think Foundry, but instead of choosing random inputs, we use symbolic execution. And ERCX, which is an automatic conformance checker for ERC20 tokens, ERC4626, ERC271 tokens. This workshop will also have some prizes. I think the top prize will be, I think, $2,500, and the top 3 participants will also get an invitation to, or get an interview at RV to apply for a formal verification position. And that's very important for me. That's my last point. We are building this debugger, and we are building it for the community. As I said, it will be open source, but we really need your feedback. Like, we are building with the community for the community. So please try it out. If there's something that you're missing, like a feature, let us know. We can make it happen, but only if we know. So stay in touch with us, like reach out. We are on Twitter, we are on Discord, we are on Telegram. Whatever channel you prefer, somebody will always respond to your feedback. Yeah, that's it. Thank you very much. Are there any questions?
Thank you for the talk. It's amazing. I'm really waiting for the debugger. And the question is it tightly coupled with Visual Studio Code, Visual Code, or it is like accessible via debug access protocol or something like this?
Yeah, that's a very good question. So our initial release focuses on Visual Studio Code, but it is built around this open standard, which is called the debug adapter protocol. So you can actually connect it, like if you are an Emacs diehard, for example, you can connect it to an Emacs IDE. You can connect it, maybe Remix can add support if they want to. We are talking with several other like online platforms providing code analysis tools online, and they want to make an integration happen. So to answer your question concisely, it's not tightly coupled to Visual Studio Code. It's all built on open standards, but for us, at Runtime Verification, we focus on the Visual Studio Code integration the most at the moment, because we know from like the Solidity developer surveys that VS Code is currently the most used IDE among Solidity developers.
Thanks.
Do we have any more questions? No? Okay,
then, yeah, have a nice lunch, everybody, and just catch me outside if you have more questions and want to talk. Thank you.
Thank you, Raoul.